So welcome everyone for this talk. Don't look at the number of slides. I mean that's a smoke screen. So we will directly begin with the thing. So we are dealing with statistical factor models here, although there are multiple factor models that have been used in finance, such as the very famous French model, which is a fundamental factor model, and then there are macroeconomic factor models where you try to model stock returns based on, say, the inflation rate, the GDP, etc., etc. Here in statistical factor models, we just try to look at the price data. That is, you have a cross section of stock prices over a long or short time series, and you want to use that particular data itself with no other help, no other data, to get certain statistical factors, certain variables, which are then going to explain the variability in the cross section of returns. Now, they have been used for different purposes. First is to decompose risk and return into different components, and the most important one is in terms of the portfolio allocation thing. That's a more interesting problem. We are not going to deal with many of these applications right now. Going to the notations straight away. So we are dealing with P stocks. Just keep in mind the notations, and N periods. N would be the samples here. RIT is the excess return of asset I. We are dealing with stocks, to be precise, again, where the excess return is actual return minus the risk-free rate. You can take the bond yields and all those things as your risk-free rates. And then you have the model being given as in the regression form. So RIT, which is the excess return, can be explained as in terms of a regression model where you have F1t till Fkt, where k is the number of factors. So and epsilon it is the idiosyncratic risk. So that is that component of the returns which cannot be explained by your statistical factors. Betas, the regression coefficients, represent the factor loadings. And also, interestingly, the P cross P covariance matrix of asset returns can be explained in terms of the factor loadings and the covariance of the factors. This would be important at some point of time. Now, when you are dealing with a low sample and high dimensional regime, you get to a situation where the number of samples is generally less than the number of assets or dimensions. Mainly because sometimes some of these stocks, when you're dealing with, say, Nifty 500, some of these stocks would go out of that index, and then there would be a new constituent there. That makes it very difficult when you are dealing with large portfolios. There are the other issues as well, such as structural break. This is PCA. I'm not going into the details of PCA, but just look at this thing that for doing a PCA, you would require to estimate the eigenvalues and the eigenvectors. This is again the sample principal components. So the factors can again be computed using the eigenvectors and the returns. Not going into the details of it once again in the interest of time. So once you get those factors from PCA, we are dealing with, so there are multiple ways you can calculate these factors. One would be the maximum likelihood method, which is generally used. Apart from that, this is a more simpler method, the PCA method. Here, if you see, once the factors are computed, you have to get the factor loadings. That is something that you get from the regression. Now, PCA cannot be performed in a low sample regime since the eigenvalue decomposition fails. You do not get meaningful eigenvalues because the covariance matrix becomes ill-conditioned, which also means it is sensitive to noise. So that is when P is much greater than N, but also when N starts up. So suppose we are dealing with, say, P is equal to 500 and N is equal to, say, 1000, and we keep decreasing this N, the number of samples, to, say, 600, 650, 550, the covariance matrix starts getting noisier, even if it's invertible. So there is a problem when you start decreasing the number of samples. There are multiple ways in which you can deal with this problem, either by getting cleaner estimates of the covariance matrix or by using an inverse covariance matrix. Now, for cleaner estimates of covariance matrix, we generally use shrinkage methods. So you have the sample covariance matrix, which is very noisy. You shrink it linearly or non-linearly with respect to a sparse target. It could be an identity matrix, it could be a constant correlation matrix, whatever. This approach has been discussed in Ledova and Wolf. So this particular paper uses linear and non-linear shrinkage in the context of PCAs. So the inverse covariance matrix is a more interesting thing, where you directly get the covariance matrix inverse using Gaussian graphical models. So the questions that are being asked in this particular paper is, right now the only alternative is the asymptotic PCA. So basically the asymptotic PCA tells you that when n becomes large, if you have k factors and you have p assets and n samples, you can, instead of using the noisy covariance matrix, you can get a you can actually take a covariance matrix of size n cross n rather than p cross p, and asymptotic results show you that the first k eigenvectors of that n cross n covariance matrix, which represents the low sample n, give you directly the factors. So that is the existing alternative. So this paper came in 1986. Now there are some more alternatives that we are talking about. Ledova will have talked about some of them, but they only talk about synthetic experiments. They don't talk about economically interpretable tests. So we build on that. This paper addresses three crucial challenges. So we compare eigenvalues properties of the covariance matrix and the precision matrix, which is quite simple. Apart from that, we try to compare the PCAs that we develop based on shrinkage and GGM based methods as an alternative to the asymptotic PCA. We do synthetic and empirical experiments. So this is GGMs for you, very basic introduction. So what it essentially tells is that the inverse of the covariance matrix encodes the information about the partial correlation between different variables. Not going into the details of it again in the interest of time. So the property that we exploit while using the inverse covariance matrix estimate is this, that the eigenvalues of theta are the reciprocal of the eigenvalues of sigma. Sigma is the covariance matrix and theta is the inverse. The eigenvectors remain the same. So so PCA goes like this, that the first principal component would be associated with the highest eigenvalue. So instead of doing that, we can take its reverse, the lowest eigenvalue. So that is how it would work. The rest of the process is very similar to standard PCA. Benchmarking of models was done using both synthetic and empirical experiments. We're going directly to the experiment designs. These are the list of models apart from the asymptotic PCA that have been used. So these are the loss functions for the empirical experiment. So this alpha represents something very similar to the CAPM model. You have Ri is equal to alpha plus Rm minus Rf. So it's a very similar alpha here as well, the intercept term basically. And then you have the total adjusted R squared. This is more important, the correlation structured, which is being measured by sphericity. This came from the psychometric literature. So basically the idea is, we assume in asset pricing that the pricing to be perfect, you need to have the errors to be independent of each other, which means that the correlation matrix of the errors should be ideally an identity matrix in that case. So here we take the determinant value of the correlation of errors. So this is the sphericity measure that we talk about. So RMS alpha and total adjusted R squared have been talked about in literature. We thought of using this one as a new sort of loss function. We use 6 years of data. Again, this is 6 years of data on a rolling window basis. We do for low sample regimes. So this is for the synthetic experiment again. We have done it for Nifty 500 and Nifty top 100. So there is something known as the eigenvalue distance, the factor coefficient distance and the factor matrix distance. So this is you calculate something from the data, from the full data that you have empirical. You get the covariance matrix, get its eigenvalues, do a PCA, get factors and all those things. And from that so-called true values, you try to measure the distance with respect to the estimated eigenvalues and other measures with respect to the models that have been talked of. So PCA is based on GGMs and shrinkage methods. These are the results for 100 and 500 dimension sizes. So if you see, interestingly, the methods which directly employ the inverse of the covariance turn out to be somewhat better than the shrinkage based methods. This is for both dimension sizes of 100 and 500. We go to so there is another thing, what factor size to choose. So we do a CNG test, a test based on the eigenvalue properties to get the optimal number of factors. This is very important. So we do it for 3, 4 and 5 actually. We have presented results only for 3 and 4 here. So we generally see that GGM based methods which directly estimate the inverse do better than the shrinkage based methods for both 3, 4 and 5 factors. So these are the results. Skipping a lot of these things right now. Conclusion is that the eigenvalue properties, the eigenvector properties are better when you take GGM based PCAs followed by shrinkage. Generally we see a pattern for shrinkage based methods. So nonlinear shrinkage that came up much later does a better job than the linear shrinkage. So this is a broad conclusion. We could also take a larger range of shrinkage methods to get a more general picture, but for this particular study there are just 2. We also do a empirical experiment where we see that we compare methods using the superior predictive, using the model confidence set method. So it's a sequential test. You have a series of loss functions which we have talked about just now. We say that a range of models have equal predictive ability. From a large range of models, we try to reject models at each step until we come to a step where we have a set of superior models. This is very helpful when you are dealing with a family of Garch models. But in this particular case, we did not have an inferior set of models. All models had more or less similar valued loss functions, and we saw that these are the rankings based on that. So broadly speaking, the greedy prune based methods have performed better than the Gaussian graphical model based methods have performed better than shrinkage methods. Although if you go to some other variables, you would see that the nonlinear shrinkage method performs better than the HMB PCA. So we have some of those results as well. So HMB PCA is a GGM based method. It relies on calculating the inverse of the covariance and then doing a PCA. So in some cases, using a nonlinear shrinkage also helps. So these are the general results for sphericity, RMS alpha, and the other variable, the adjusted R squared. So we have also done experiments for the 4-factor and 5-factor model for different dimensions, for other dimension sizes also, say Nifty 50 and Nifty 200 and all those things. But yeah, this is a summary of the results that we have. So broadly we see that in terms of economically interpretable variables, greedy prune, the GGM based methods performed better than the shrinkage based methods. Asset pricing is better when you use GGMs. The other part of this question is, why do you even need a statistical factor model? So ideally you can use statistical factor model when you are dealing with large dimensional portfolios. Instead of using your sigma, which is the covariance matrix, you can actually, as we had seen in a previous equation, you can decompose it into a covariance of the factors times the factor loadings and the error terms basically. So in that particular context, you can also do a factor based portfolio allocation and compare it with, say, the the usual mean variance portfolio optimization framework of Markowitz. So that would be an application of this. There are multiple other applications. So these are the broad conclusions from this study. So in interest of time, I would conclude the talk.